Okay, so let's take a look at some specific fossil fuels. Fossil fuels provide most of the world's energy, and you keep hearing me talk about coal, oil, and natural gas. They come from deposits of organic material that was formed 50 to 350 million years ago in an anaerobic, not oxygen environment. And they're carbon sinks, they're storage of carbon. We're going to start with coal. Coal is a solid fuel formed primarily from the remains of trees and ferns and other plant materials from 280 to 360 million years ago. There are 4 types, ranked from lesser to greater age, exposure to pressure and energy content. And the 4 types are lignite, subbituminous, bituminous coal, and anthracite. Peat is a precursor to coal. It's composed largely of partly decomposed organic matter, and our largest coal reserves are in the U.S., Russia, China, and India. If we look at how coal is formed, the vegetation dies, it's buried under anaerobic conditions, it's compressed, then there's further compression and even more compression, which leads to the different types of coal. If we look at some of the advantages and disadvantages of coal, advantages, it's energy dense, it's plentiful. We access it by surface mining, which is low tech. If we have to move to subsurface mining, it increases technology and human health consequences. But surface mining is pretty low tech. We're just digging it up. It's easy to handle, and it needs little refining. Some of these disadvantages are there's impurities, and one of the big ones is sulfur. Sulfur will then put sulfur dioxides into the atmosphere, which will lead to acid rain. It combines with that hydrogen, makes sort of an H2SO4. There's also mercury, lead, arsenic. There's lots of ash remaining, and it's going to put a lot of carbon dioxide into the atmosphere. This is the New Jersey profile of exposures to coal-fired power plants, and you can sort of see the population and what areas. You can see the red dots represent our power plants in a 30-mile radius. If you look at the northern part of Hunterdon County, we're not in that area, that exposure, that 30-mile radius. Petroleum. So if we're looking at petroleum and we're looking at crude oil, petroleum is a fluid mixture of hydrocarbons, water, and sulfur that occurs in underground deposits. It's formed from the remains of ocean-dwelling phytoplankton that died 50 to 150 million years ago. It also contains natural gas, and a lot of times when you see a well, you'll see that flare at the top, that gas flare, and that's to prevent explosions. They have to burn some of that off as they're harvesting it. Crude oil is liquid petroleum that is removed from the ground, and we sort of use those 2 words fairly interchangeably. So you can see if we have a well that's tapped, the top part of that well is typically natural gas, and so that's why there's often a flame at the top. So we can harvest both forms. We can harvest both the oil and the natural gas from these sources. The U.S. uses 816 million gallons of petroleum products per day. Most of that is for transportation. If we're going to look at some of the advantages and disadvantages, petroleum is easy to transport and use. It's a liquid. It's very energy dense. It's cleaner burning than coal. The disadvantages is that it's also still going to put CO2 and sulfur into the atmosphere, although it can be refined to put less sulfur into the atmosphere. Oil comes from beneath the ground or the ocean, and so anytime we have to transport it, we have the opportunity for leaks to occur. 85% of oil spills comes from some sort of runoff. More than these major spills that we have talked about, a lot of it is just small amounts of runoff from various forms of transportations and shipping. One of the big concerns in terms of transporting petroleum is the Trans-Alaska Pipeline. They want to run it through ANWR, you'll hear it here, is the Arctic National Wildlife Refuge. But knowing that putting this through this pristine area, there's the potential for leaks. If you're looking at natural gas, what is natural gas? It's found with petroleum or alone. It's 85 to 90% methane. The other 5 to 20% is ethane, propane, and butane. It lies above the oil, and its biggest use is electricity and industrial processes. It's also used in the manufacture of nitrogen fertilizer and in residences directly. It must be transported by pipeline, And then if we look at something called LPG, which is liquefied petroleum gas, it's slightly less energy dense, but can be transported via truck and stored in tanks. And it provides 24% of the U.S. energy. So this is the kind of stuff that's in your barbecue grills or things that are in heaters. Some of the advantages and disadvantages of natural gas. It's used in half the homes in the United States due to an extensive pipeline system. It has fewer impurities and it has no sulfur or particulates. It also has less carbon dioxide than coal and other sources. Some of the disadvantages is that the unburned natural gas, the methane, escapes, and that's one of the worst greenhouse gases, just that in itself. When you need things like the thumper trucks that are drilling and opening up rock containing natural gas, that's referred to as fracking. You're drilling with water and sand and proprietary chemicals that we're not privy to. It takes lots and lots of water used, and there's a high chance of contaminating groundwater in harvesting that. And then if we're going to look at things like oil sands and liquefied coal. Okay, so if we're looking at oil sands are slow-flowing, viscous deposits of bitumen, which is tar or pitch, a form of degraded petroleum that's mixed with sand, water, and clay. Could extend our petroleum supply, serious negative environmental impacts. It's more energy to mine. It contaminates water. It requires a lot of processing. The other thing that we have is this coal to liquid. It's expensive to do. It's a large greenhouse gas. It's taking coal and essentially liquefying it so that we can treat it kind of like oil. But it's very expensive to do, and you put a lot of energy in to make that happen. Fossil fuels are a finite resource. Energy intensity is the energy per unit of gross domestic product. Energy can be used more efficiently, but we have more people, so therefore we have more energy used. If we look at this idea, this Hubbert Curve, this is from 1969. Hubbert projected a point at which oil production would reach a maximum and the point at which we would run out of oil. He used two estimates, an upper estimate and a lower estimate. He sort of guessed that oil extraction and use would increase steadily. And when we reach peak oil, half of the supply is used. Okay. Hubbert predicted that 80% of the world's oil would be used in 60 years, and that's 60 years from about 1970. So we're looking at being past peak oil. How long will our fossil fuels last? If global patterns continue, we'll run out of conventional oil supplies in less than 40 years. Natural gas supplies will last slightly longer. Coal supplies will last at least 200 years. Some of the current motivations moving to renewable energy sources, things like global climate change. We're starting to see that this is a problem, that it's anthropogenic. That means humans are causing it. It's not when will we run out, but how will we transition to the next phase of energy. There's concerns about scarcity, the environmental impacts such as the carbon dioxide being produced, and rising oil prices. So the next one that we're going to look at is another conventional non-renewable fuel that does not significantly add to greenhouse gases, and this is nuclear energy. So nuclear energy is fission, which is nuclear reaction in which neutron strikes a relatively large atomic nucleus and splits into two or more parts. It releases additional neutrons and heat energy. It leads to a chain reaction, and the nuclear reactor will harness that energy. The byproduct of this is nuclear waste or radioactive waste. We need to understand how a nuclear reactor works. This is a core idea. Again, we're going to generate steam to turn a turbine. That is the gist of energy production. So we have this containment structure that encloses the nuclear fuel and the fuel rods. There's hundreds of them at the reactor core. So we have those control rods. The fuel rods are interspersed in between them. The heat from the nuclear fission is used to heat the water. It produces steam. It turns a turbine, which turns a generator. The plant's job, the nuclear power plant's job, is to slow that reaction. The control rods, which are cylindrical devices that are between the fuel rods, are used to absorb excess neutrons and slow the fission reaction. If it's left uncontrolled, it can become too hot and lead to meltdown. The advantages and disadvantages of nuclear energy. Well, some of the disadvantages, it takes 900 kilograms, 2,000 pounds of uranium ore to produce 6 pounds of nuclear fuel. So we have to do a lot of mining to get just a little bit of fuel. And the slag, is the stuff that we need, uranium-235, but most of it is uranium-238. Nuclear power plants are really expensive due to protests and locations for nuclear waste. It became too expensive after 1980 to actually create new nuclear power plants. All the ones we have were commissioned in 1980 or earlier. Advantages to nuclear energy: no air pollution. It allows us to have some energy independence from fossil fuels. 70% of France's energy is by nuclear energy, but only 20% in the United States. There's 104 plants in the U.S. There's no carbon dioxide that's produced except in the mining, constructing, and processing of that nuclear fuel. This is a tour of Chernobyl, which is one of the nuclear disasters that occurred. In April 26, 1986, Chernobyl in the Ukraine, a test of the plant. The operators deliberately disconnected emergency cooling systems and removed the control rods, which led to an explosion, damage, 31 deaths from acute radiation, and many, many more to cancer. Fukushima is also another major. 6 reactors were affected. That's when there was an earthquake off the coast of Japan. Full meltdown of 3 of the reactors. There was an attempt to use seawater to cool the reactors. That ruined it. Other concerns: the water levels in the fuel rod pools. The total reactivity released was 1/10 that of Chernobyl. Most at risk were workers, and young people are always more susceptible. Tens of thousands evacuated from that, so there was the magnitude on Friday, and if you can sort of watch these power plants, they went down the line and exploded on Saturday, then exploded on Monday, and then 2 of them exploded on Tuesday after that quake. So we try not to build nuclear power plants where there's potential for natural disasters, but it can happen. Nuclear power plants that are near us, you could see what the fallout radius is. So those are some of the nuclear power plants. And you can sort of see about where we are. We are in the range for fallout from if a nuclear power plant were to melt down. Radioactive waste. Long after the nuclear fuel produces energy, the radioactive waste. There's high-level waste, such as used fuel rods, and then there's low-level waste, things like contaminated clothes or tools. The half-life for radioactive waste that's used in nuclear power plants is 704 million years. Currently, spent fuel rods must be stored on site. It cannot be incinerated or safely destroyed. Waste must stay in the earth. We can't let it get into the groundwater. We have to store it somewhere that is safe from nuclear attack or from terrorist attacks. Possibilities are Arctic ice sheets beneath the ocean floor. Space isn't a real viable option. Yucca Mountain was proposed in 1978. It's a site that is 90 miles northwest of Las Vegas. In 2006, it was determined that would be our best long-term repository, but the project was canceled. There was too many protests, even though it was considered to be safe. People of Las Vegas did not want nuclear waste stored 90 miles from them. If we decommission nuclear power plants, they're licensed to operate for 40 years. Several have received 20 years extensions. They can't be abandoned when they're shut down. What can we do with them? We can use them for storage. We can use them for entombment, and we can decommission or dismantle them. Average age of some of the nuclear reactors, looking at different countries as of August 2009, the average age in China is 8. Looking in Sweden, they're 31 years. So, we're reaching, and add time onto that because this is as of August 2009. Looking at some aging nuclear power plants, you can see roughly where they are located. Looking at the years of operation, we have very few in that 10 to 19 range because we stopped producing them in 1980. Quite a few in the 20 to 29 range, and quite a few in that 30 to 39 range. Fusion is our last thing. What is nuclear fusion? Nuclear fusion is reaction that powers the star.